very close to 0, okay, you can take the limit, okay, because you already all this calculation. So you can take the limit, okay, then you can construct the linear stable manifold and and linear unstable manifold, etc. Okay, and now use the coordinate of center stable manifold. You can write down as a coordinate system to write down the linear unstable center stable manifold of this linear problem. So eventually you can reduce the diagram of the linear the nonlinear center stable manifold. Okay, and now in this case, okay, you will see the cell. Okay, so this way the whole picture is this is infinite dimensional space. Okay, and now here this 9, okay, is a center manifold. Okay, now I say here the center manifold is a 4-dimensional. Okay, you have these is a 4-dimensional variable. Okay, if you fix the space dimension 1. Okay, and then, but however you have a 4 conservation law. Okay, so this is 4 conversion. This 4 conservation law. It reduces this 4-dimensional center manifold into 1-dimensional. Okay, so now it's so good. Okay, so that means eventually you can take a reduction of the center stable manifold. Okay, with a core dimension 1. Okay, so this one is a 1-dimensional invariant manifold. So that turns out that so now you want to look in all the Shih structure. Okay, you can restrict to this 1-dimensional problem. So now before our equation for the Shih profile is an infinite dimensional problem, and after this reduction, it becomes a 1-dimensional ODE Berger equation, almost like a Berger equation. Everybody can solve it. So now by using this one, you can solve the existence of the Shih profile, and you also prove that the Shih profile is monotone by the coordinate on this center manifold. Okay, and now you also can see here, because at each point, okay, there is invariant manifold of core dimension 1. Okay? And so and here at this another fixed point, okay, there is also invariant manifold of core dimension 1. So by this picture you will see that if every state defined in here, then you will eventually converge to the one equilibrium state, and everything outside here will go out, go in, and then we define. We use this two picture, these two invariant manifold we define is as a Solomon manifold. We use this one as a machinery to solve the boundary value problem. So this means the boundary value problem is look at the minus problem with a given problem. So with this notion of the center stable manifold, you can define a function defined in terms of the far field, in terms of the far field of the Maxwellian. Okay? So you given a fixed boundary data, and you choose a far field of Maxwellian. So you can define a map from this given boundary data to the say in the center stable manifold. Okay? And then you can find out a criteria. Okay? If the state in some region there's solution, and in some region there's no solution. So you solve this bifurcation problem. Okay? And now the other application of this Green's function. Okay, you can use this one to study the time-dependent problem, because your Green function was devised for the boundary problem. So this is quite a routine. So you can use the Green function to show the linear stability of Maxwellian state in the half space. Okay, and then and then you can actually the same tool can push a little bit to replace a Maxwellian state at the boundary layer, and also show the stability of the boundary layer so this is for the hardest field with the angular cutoff. And And then you say, okay, and then you using the green function, okay, and then you can use it to solve the stability or sharp profile. And actually now the only difference is that you replace the linearization around a constant state. You just linearize around a sharp layer. So okay, so using the far field structure, okay, you can use it to construct the Green's function for the proper linear around sharp. So you can see okay, so here just illustrate, okay. So you can see all this wave propagation for proper linear around the sharp. So everything is go inward, okay, hit the sharp and the reaction some way and then reflect back. Okay, so you got those fine structure of under this linear label, and the plugin it's just a matter of the analysis to improve the nonlinear stability. And this one also used, okay, you can use this one to solve the Riemann problem. So now as a consequence, okay, I mean the Green's function is so powerful. And now here the main thing is that okay, we use the information. Okay, so what do I mean the Green function? It means we know all the characteristic curve, okay, how is play is law in terms of the Boltzmann equation. So in here we have very good understanding on the PDE in one space dimension. Okay? And so what will be the next? Okay? Is we need more of information. Okay? So now I mean we starting from the space dimension 5. Okay? Now you want to go further to higher space dimension. Okay? So we better have, okay, and then for the solution of PDE in the multi-D, it's a completely different game. For example, I mean for one dimension, everything just go along a straight line, and for the PDE in the multi-D, everything becomes like a chord. Okay? So go like here and become so here it will go out and then reflect back and become this pattern. And then for example, okay, so here you have some obstacle, and then so I have some way go toward this direction, a kind of diffraction, okay, got all the circle, etc. Okay. So now at least, but however, the PD, okay, the PD series on this stage is still needed a further development. So I think okay, that if we want to go further, we better have a good understanding on all this basic PD. And now, at the same time, okay, how is it related to the Boltzmann equation? Okay, what would be interesting? Okay, so for example, if you look at it, it's one dimension, one space dimension. Okay, so then you can refer what happened in the initial boundary problem. Okay, and then the solution is not stated in the first diagram by the Hsien's classification problem. Then it's also an interesting problem. Okay. And also maybe the most challenging maybe in the future, okay, say like this a reentry problem, okay, say this is like a satellite from the outer space enter the air, okay, so then you can see there's some part of it, so this you can see go down here, okay, all the equation up here is a vacuum in the main door with this layer is a kinetic equation. Okay, this I learned this picture when I was a student typing talk about the Boltzmann equation. Okay. It's a picture like this, and I think okay in the long this the connection from the vacuum to the kinetic equation and to the Euler equation, how to connect these three branches of physics in terms of mathematical theory. It will be very interesting and challenging problem, and also how to study the wave equation and the hyperbolic equation in the multi-D with the presence of boundary, and this is also quite interesting and challenging problem for the future. I think I will stop my talk here.
Is there any question? Comment.
There was this kind of discussion that I come upon in 1949, and Heisenberg raised the question of the vacuum boundary. I guess it's a central question. Even Heisenberg, after all the quantum mechanics, he raised it in front of von Neumann.
Yeah.
You know that panel discussion, yeah. Because you have all this picture of a postman, Peter Lux, Hessenberg is a good guy.
Oh yeah, I work with TV also on common.
About common, that's true. He also mentioned this.
Yeah, it means that there's no boundary, there's no room mechanics.
I think let's start with the Guangzhou. Someone told me the other day, is that Guangzhou was an advisor of the Quantum. Is that true?
Yeah.
Is perspective in microscopic terms very distinct from that of macroscopic terms.
Can you say again? Okay, can you speak Chinese?
微观的观念跟巨观的观念有很多不一样吗？
Okay, the macroscopic this part is essentially related to Euler equation. Okay, and the microscopic depends on what setting of problem. For the Boltzmann equation, you can say is the fluctuation. And there is many freedom to define what is the microscopic. It depends on what kind of equation you are looking at. So if the problem has a many different scales, okay, you can distinguish the macro and micro. You might say, okay, the macro part is related to the small decaying rate in space and time, and the microscopic is a fast decaying rate. So this means it's up to you. It's actually it's just amazing is a scale splitting.
And therefore, we discuss the perspective in the microscopic scales rather different from macroscopic scales.
Well, because you already separate it. Okay, you already separate it, so it's different. It's different.
So one of your results proves the stability of the shock wave of the Boltzmann equations. So can these results also provide another proof of the stability of shock wave of conservation laws? Is that possible?
Yeah, it should work. Yeah. Because in the proof we do not use so many structure of the Boltzmann equation. Essentially, we use the structure is universal.
Any further questions? If there's no, it's time to speak again for